Welcome to your lesson on current electricity. Let's jump straight into it. And just a reminder, in our last lesson we were talking about static electricity. I just want to remind you that static electricity is when you can build up a charge and that charge stays put, stays in one place. So if you had your balloon and you rubbed it on your hair, the negative charges would transfer from your hair to the balloon, but it would only stay charged in the one location. If you didn't rub on the other side, there would be still a neutral charge over here. The negatives will stay put. So static, stays put, stationary charge, okay? That's exactly opposite to what happens with current electricity. With current electricity, you're going to see a flow of electrons. You're going to allow the electrons to move through the material, but that'll only happen in something called a closed circuit. So we'll be talking more about that as we move along. In a closed circuit, the electrons can move from where there is a negative area, so we had a buildup of electrons, to where there's a positive area or a lack of electrons. So negatives move to where things are positive. Okay? That'll make more sense again as we start to explore batteries and as we start to do actual circuits and whatnot. The main point of moving these electrons is to return the balance back to neutral. If we can get the negatives to go where the positives are and we have an equal number of them, we're back to neutral. Now, a couple little terms you need to know. We've introduced them before, but they are very important for this lesson as well. You have an insulator, which does not allow electricity to be conducted through it. These are your classic nonmetals. You were messing with these last week when you were doing your experiments. So the rubber balloon or a piece of wood or some plastic or styrofoam, these are all made primarily of nonmetals, and these particular guys will allow static to build up on them. So just like the balloon up here at the top, the static stays where you put it. Okay? So negative charges could build up, or if I was to steal these electrons, then a positive charge would be there, but it would be in a local area. Okay? Just not allow electricity to be conducted through it is the key point. Okay? Then we get a conductor, and obviously conductors conduct. Any material that can conduct electricity will conduct electricity, and that'll create something called a current. Current just means the flow. Okay? All metals can do this. Some do it better or more efficiently than others, but all can do it. And even some of the metalloids, these are the elements that are on the staircase in the periodic table. We would call these guys, because they're not quite as good as metals at conducting electricity, and they're way better than non-metal, we call these semiconductors. They allow electrons to flow, but they slow the current just enough to allow us to do some pretty cool things with electricity. Slowing the current is called resisting. We resist the current. And a famous metalloid that's used in any kind of circuit is silicon. Very, very good semiconductor. Great for computer chips and all sorts of things. Now current, if we're going to measure it, we're going to measure it in something called amperes, or you've probably heard of it as amps before. The unit symbol that we would use is a capital A. The case matters, has to be a capital A. And really what it is it's the amount of charge, or coulomb, the amount of charge flowing past the point in 1 second. Please memorize the fact that current is charge per second. It'll help you out when we start to do calculations in a few days from now. Okay. Now I forgot to write it in here, but it will use an ammeter, which is this word right here. Ammeter goes in this blank here. So ammeters have to be placed in something called series, which we'll cover another day, but it basically means that if you want to know what the current is flowing through this particular device here, which in this case is a light bulb, you have to put the wires in between the thing that you're testing and the battery, because the current has to flow through this guy here. Okay, it's going to flow from the negative end and flow through the ammeter back to the battery. Right? Now there are 4 main parts of a circuit. There are other things we could add in, but in general we categorize them in 4 parts. You get a load, which is basically the thing that's using the electricity. You would normally call that an appliance. So the computer that you're looking at right now, or the phone or whatever it is you're using to watch this, that's your appliance or your load. It's the thing that's using the electricity. It's going to take the electrical energy and convert it to other types of energy. So the fact that you can see this right now means it's been converted to light. You probably are listening to me right now, I hope so anyway, so you know that the electrical energy has been converted to sound in this video, right? Etc., etc. Wires, of course, you know what those are. Those are just connecting the parts of the circuit. These are made of conductive material so that you have a pathway for the electricity to flow. Then, of course, you need a power source. This is where your electricity is made. We'll talk more about this over the coming days, but the basic idea is that you need to have a charge separation. That's a fancy way of saying something needs to become positive and something needs to become negative, because we want to have a selection or a deposit of electrons that will then move to the positive area. So you want to build up electrons on one part and then they'll flow to the other part. Okay? So then we have batteries that can do that for us. Batteries are getting better and better, way better than they used to be, way more powerful than they used to be. Power plants obviously doing that, and generators obviously doing that for us, creating a charge separation so that we can get the flow of electrons to a positive end. Then, of course, we have a switch. You do not have to have a switch in order to have a circuit. So the main parts of the circuit would be you must have something using the electricity, you must have wires, and you must have a power source. Okay? These are all essential to having a safe circuit. But if you want to control whether that circuit is turned on or turned off, then you throw in a switch. An open circuit is one where the switch doesn't connect, and you'll see that in the next page here. It doesn't connect, and that stops the flow of electricity. So there's a break in the circuit, a break in the current. A closed circuit then is one that electricity can flow through. So basically you have an open switch and a closed switch, open circuits and closed circuits. Now, I just want to mention before I move on, if you don't have a load in your circuit, you just have wires and a power source, you're in big trouble. That's something called a short circuit. And what can happen is the wires themselves are going to heat up, and you can actually cause fires in your houses and burn down a house from a loose connection with wires where it no longer goes to the load. You just have the power feeding through the wire, feeding through the wire, feeding through the wire, heating it up to such a point where it actually causes the wood that it's attached to combust. It gets too hot. So it's very important that whenever you are creating a circuit, you always make sure you have something using the electricity. Don't just connect wires and a power source. That can be very dangerous. You don't want a short circuit. Here's some of the symbols that we're going to use. We'll add a few more symbols as we go along, but these are important for you to memorize and learn how to draw today and when you're doing lesson 20 as your homework. Okay. So for loads, some examples are you could have a motor, and you notice it's M in the circle and then the two lines on the side, and then these lines here show the wires coming out. You have a light. It's easiest if you draw the circle first and then you do this little cursive L to sort of show the light bulb. The resistor is always a little tricky to remember, but think of it as 3 mountain peaks. So make sure that they all kind of go up and down the same amount, but you've got the first peak and then down to a valley, middle mountain, down to a valley, third mountain, and then you're level again. Okay, so try to do well on drawing these symbols here. Then, of course, you got your wires. That's the easiest. That's just a line. Now, the power sources are going to come in different numbers of what we call cells or a battery. If you want to think of your regular AAA battery or AA battery, that's a single cell. But if you stick a bunch of batteries together, so for example, if you've got a mouse for your computer and it happens to need 2 batteries in there, 2 1.5 volt AAA batteries or whatever, then you would actually have 2 cells back to back in the circuit. So 1 cell, 2 cells. You can even have triple cells and quadruple cells or whatever. But this is, you need to learn how to do this. So it would be a short and a long. The short part is the positive end, and the long one is the negative end. I've drawn that down below, and you'll see that again. But you can add that to your note as well right now. So this is positive, this is the negative end. Now here's what I was talking before about open versus closed switch. An open switch, notice that this is made of some kind of metal, but notice that it doesn't connect. It's broken the circuit here. It's open, it's not attached. No electricity can flow in an open circuit. Closed circuit though, the switch will make contact with the wire on the other side, and now I've got electricity, has a path to flow through. We're also going to get into voltmeters and ammeters, but not so much today. I just want to mention the symbols today, and we'll get to how to use voltmeters another day. Now, a voltmeter is going to measure something called voltage. You've heard of that before, I'm sure, but maybe you don't quite know what voltage is. So I'll jump into that a little bit in a second, and we'll do it in a completely different lesson as well. An ammeter is the thing that measures the current. That's the amount of charge per second. So current. So volts and amps are what we're going to be dealing with over the next few days. So potential difference. Potential difference, you have to understand the difference between potential energy and kinetic energy before you can understand the term potential difference. It is exactly the same thing as the word voltage. Voltage is just naming potential difference after Volta, who was a fancy dude who figured out a lot of stuff about batteries, so he gets a lot of credit. So first of all, potential energy is energy that gets stored in an object, whereas kinetic energy is the energy of that object moving. As soon as that begins to move, the potential energy gets converted to kinetic energy. So here's a simple little example. You've got an apple. The apple is still sitting in the tree. While it's above the ground, it has potential energy because if it breaks off the tree, it can begin to move. So we say that there's energy stored in there. It's the energy of its position, its height, and it's stored in there. And as soon as it begins to fall, its potential energy gets converted to kinetic energy. So by the time it lands, it's got a lot less potential energy because it's all been used up to move that sucker. Okay? But if I pick up the apple and I lift it up again, I have added its potential back in. So it'll have potential energy depending on how far away it is from the ground. You can sort of get the idea of how much energy is stored in an object versus height. If you think about the idea that if you're down here at this level and you drop the apple, you might not even bruise it. You might just fall and be fine. But if you go to the top and then you drop the apple, you've got a lot farther to fall, which means that the apple had much higher potential energy, so that when it actually lands on the ground, all that energy got converted, and you're going to smush that thing. It's going to be apples in pieces, not just an apple maybe slightly bruised. So potential energy, as you go higher in position, farther away, you're going to have a much, much, much greater energy store that you can then convert to a different type of energy. So we'd like to take this idea of potential energy to try to explain what's happening inside a battery. The batteries have potential energy. They are a combination of what we call electrochemical cells. Okay, electrochemical cells, basically compartments, cells or compartments, where we're using chemicals to try to produce some electricity. So they've got a package of chemicals inside them that are going to convert chemical energy to electrical energy. So really, what are those chemicals? Well, you've got in the one part, you have something called an electrolyte. An electrolyte is either a liquid or a paste that helps to conduct electricity. So you're going to get little ions moving between the one part and the other, flowing through the electrolyte. Batteries do not work if there's no electrolyte. Now, if it's a liquid version of electrolyte, you call it a wet cell. If it's made from more like a paste, then the battery is called a dry cell. The batteries that you're using in your cell phone, in your whatever you've got, those batteries that you have at home, the ones that you would normally call a battery, those are dry cells. They have a paste inside, not liquid. Right? Now, the chemicals in the electrolyte are going to form ions. And if you remember from our chemistry unit, ions are charged particles. Okay? Now, ions could be positive. They could be cation, or they could be negative ions or anions. Remember that terminology from the first unit. But either way, they're either going to be gaining or losing electrons. Okay? That's key. Somebody's going to gain an electron. If they do, they become negative, and somebody's going to lose an electron and become positive. This is what we mean by charge separation. You begin to build up negatives in one part of the battery, and you have positives being left behind in the other part of the battery. The bigger the difference is between the negative and the positives, the bigger the flow of electrons is going to be. That's very similar to what we saw in static electricity. If you have a very large difference in the charges, so for example, what builds up on the underside of the cloud when you're about to have a lightning strike, you get all those negative charges on the bottom of the cloud, which forces or induces a charge on the ground, making the ground temporarily positive, and suddenly you've got a massive charge difference and a huge bolt of lightning as the charges transfer from the negative cloud to the ground, to the positive ground. But if you only have, let's say it's your sock versus the carpet, well, you're not going to build up a huge charge, so you're only going to have a little spark when you discharge. Okay? So a similar idea here. The more negative one part can become, that means the other part becomes even more positive. I'm going to get even more juice to be able to flow to the positive end from the negative end. I just want to remind you, though, that electrons can move, between atoms. Remember, they're sitting out in the orbit of an atom, but we're not talking about the protons themselves moving between atoms. We want the protons to stay put, because if we change the protons in the nucleus, then we've literally changed the atom, and we're not changing atoms here. But I do want to point out that if the entire atom itself has a positive charge, the entire atom can move. I'm just not trying to steal protons from inside the nucleus of the atom. They stay put, and then all together the protons as a nucleus are able to move. And that's the full ion. Okay, so let me say that again. The electrons are able to move between atoms, no problem, but the protons stay put. However, positively charged ions, the entire package, can lose electrons, and then that can move, just not the protons themselves from inside the nucleus. Okay, so we had the electrolyte, which is the liquid or paste that's going to help us conduct electricity, but they have to conduct the electricity from a starting point and an end point, and those starting and end points are the electrodes. They're usually made of metal, although you can also get other versions of electrodes like carbon. But they're usually made of metal, like zinc or copper or nickel, cadmium. You've probably heard of nickel-cadmium batteries. That's probably the type of battery that you have, that you're using at home most of the time. And zinc-copper batteries as well. During the reaction, you're going to have electrons collecting on one of the electrodes. So when they begin to build up on an electrode, that electrode becomes negatively charged. The other electrodes, you have two of them, has therefore lost electrons, and it's going to make its charge positive. There's a much nicer diagram in the textbook on page 435, so make sure you take a look at that. And it's much prettier than my diagram, but and it's got all the written explanation as well. But let me just quickly run through what this diagram is talking about. You've all seen the shape of a battery. You know it's got that little bump on the one side and then a flat end on the other side. What you may not know is kind of what the composition of this is. So on this bumped end, it's attached to an electrode, and then the negative end is attached to a different electrode. These are not physically touching, okay? Not physically touching. In between them, what I've drawn here in the yellow is the electrolyte paste. This is a dry cell, so it's a paste, not a liquid. It's this paste here. And basically what you have is that this electrode here versus this electrode down here on the negative end, this electrode has a much greater love for electrons than this electrode does. So basically what begins to happen is the electrolyte paste is going to be basically the pathway for the electrons to move from this electrode and then be stuck onto this electrode right here. Now, as it is with the battery just sitting here like this, you're just going to have a charge separation build up, so you have a very positive end and a very negative end. But if I took a wire and attached it to a load and then attached it back to the other end, I would begin to see these negative electrons flow through the wire and come back to the positive end, because these guys will have an excess, they'll need somewhere to go, and these guys are able to receive more electrons. So you'll see them begin to go through, and there'll be a pathway. Now, because this is an actual piece of metal, what's really happening here is a chemical reaction. We would say that because this electrode right here is losing electrons, we would say that this guy is becoming oxidized. That's the fancy term for losing electrons. Okay? The fancy term for gaining electrons is reduced. You really need to know these terms: oxidized, reduced. It'll help you with this unit, but it'll also help you literally in every other year in science if you already know what oxidation and reduction means. Okay, so this guy becomes oxidized. It's going to lose its electrons to the other electrode, who becomes reduced. One of the nice little ways to remember this, and your chemistry teacher next year or the year after might tell you, is to remember these little words here: oil rig. So you remember that oxidation is losing, reduction is gaining, RIG, reduction is gaining. And if you don't remember oil rig, you might remember Leo-Ger. Losing electrons, oxidation. Gaining electrons is reduction. So either way, try to memorize one of these two here to help you remember which is which. But you need to know you're going to be transferring electrons from the one electrode to the other to build up a charge. Now you know that batteries can get weaker and they can die. And the reason that they're doing that is because over time, if they are just a regular, what's called an alkaline battery, then these electrons are really only flowing in one direction. And when this electrode here becomes completely oxidized, it means it has no more supply of electrons to give away. It can't give any more away, then this guy can't gain anymore, and then I'll no longer have a charge separation. I can't keep separating charges. I'm not going to be able to keep producing electricity. Okay. So in an alkaline battery, alkaline because it's basic, you'll learn more about that in grade 10. The chemical reactions are only going to flow in one direction and they cannot be reversed. Okay? You're always going to flow from the positive to the negative electrodes. So the positive to the negative electrode. And that battery will die because it's going to run out of chemical fuel and it can't separate charges anymore. And again, that's because the electrode that's being oxidized, it gets fully oxidized and can't supply any more electrons. Rechargeable batteries, on the other hand, I know you've heard of those before, they use a different type of electrolyte and a different type of electrode. It's made of different materials. Usually it's made of nickel and cadmium. Those are your two different versions. And sometimes it's a lithium ion. Usually cell phones are charged by lithium ions, batteries. Okay? The chemical reaction can be reversed, but you can only reverse it by forcing the electrons to be added back in by using current electricity. This is why you'd have to plug these guys into the wall to be recharged. And basically what they do is they force this reaction to go back in the other direction so that you've got electrons being placed back onto this electrode. You're actually reducing it because you're giving it electrons, and then the electrons are now available to keep jumping back to this guy here. So then that's the recharging. Now you can't do that indefinitely. Depending on the quality of the actual battery itself, the rechargeable battery, maybe some of them that are lower quality, maybe your dollar store rechargeables, maybe you can get 100 times that you can recharge those. Newer batteries, better ones, the higher quality batteries, maybe you can recharge them 1,000 times or a few thousand times. In the future, what we're hoping is that some of these batteries will be able to be charged hundreds of thousands of times. But we're not there yet. We're still learning the technology of trying to make batteries. Batteries is actually a really big business. If you can make a better battery, man, everybody's going to want your technology. You can make a ton of cash. So maybe consider that as a future career. Right? So basic idea then, again, batteries, 2 electrodes, the paste is in between. I'm going to build up a charge so that I can have a store of electrons that I can then use, and you'll get them to flow through something and come back to here. You've got your non-rechargeable alkaline batteries and your rechargeable batteries, which have a different components, different electrolyte paste, and a different type of electrode. Go ahead and do lesson 20. It's attached to our Google Classroom. And if you have any questions, let me know. Enjoy your day.